Hello everyone, welcome to a series of static time analysis by VLSI Academia. In this video, we will see the inputs to the static timing analysis and the steps after which the static time analysis is done in the digital design flow. So before starting with the inputs to the static timing analysis, we will see a brief introduction about static timing analysis. As in the previous video, we have already described about study time analysis in a very descriptive way. So we'll just take an definition of study time analysis and then we'll move on to inputs. So study time analysis is a method of checking the timing performance of a digital circuit. It checks if all the signal in the circuits arrive at the right time and at the right place. It does this by calculating the time it takes for each signals to travel through a circuit and checking if it is meeting the timing constraint or not. So now we will see the inputs to static time analysis. The first input to static time analysis is SDF file. So SDF file is a file format used to represent the timing information of various component in interconnection within the integrated circuit design. It's a standardized format that help in describing the timing characteristic of the digital circuit. And this timing characteristic is very crucial for the proper simulation, verification, and especially synthesis of the VLSI design. The next input to static timing analysis is SDC file. SDC file is nothing, it's a synopsis design constraint file. So it's a file format which is used to specify the various constraint and timing information for the synthesis and implementation of digital integrated circuit. This SDC file is basically primarily used by the EDA tools to guide the synthesis, place and route, and static time analysis process throughout the design flow. Next is SPEF file. SPEF file stands for Standard Parasitic Extraction Format. So as the name suggests, is the file which has information about the parasitics of the circuit. So SPEC file are basically used by the STA tools to calculate and analyze the effect of parasitics on the signal propagation delays. By including these parasitic information from the SPEC files, STA tool can provide more accurate timing analysis results and help designer to ensure that their design will meet the timing requirement. SPEC files are also used to calculate signal delays caused by the parasitic capacitance and resistance. This information is really crucial in estimating the signal arrival time and whether that signal is meeting the timing constraints or not. Note that those timing constraints that I'm talking about is mentioned in the SDC files that I just now discussed. So all those parasitic elements such as capacitance, resistance, these basically affect the signal behavior and timing performance of the digital circuit. And these SPEF files are used to model and represent their effect accurately and do the timing analysis. Next input to static time analysis is a library file or a .lib file. So this .lib is a library file that contains the information about the standard cell libraries used in our digital circuit design. It is a crucial component in the process of designing and optimizing integrated circuit. So as the name itself suggests, the term library, this term library basically refers to the collection of predefined, pre-designed, and pre-characterized digital logic cells, each of which perform a specific functions. So such as NAND gate, AND gate, flip-flop, OR gate, all those things, all those gates informations are stored in these library files. This library file is used to it is used to store information about the electrical and timing characteristic of standard cells, which is the basic building block of any digital integrated circuits. As we also know that any digital integrated circuits, it basically consists, or I'll say in another way, the basic building block of any digital circuit is a standard cells. So this library file basically consists the information about the timing and the electrical and timing characteristic of those cylinder cells. Also, these library files are typically provided by the semiconductor foundries because those are the people who knows the information about the cylinder cells. And whenever you are doing any design, RTL design, or whenever you're doing any digital design, you design it based on some technology nodes. So these electrical and timing constraint of the standard cells is basically depends on the tech node that you are following for your digital design. So these library files are used by the EDA tools during the design and synthesis phase. Next input to this study time analysis is a netlist or a RTL file. So RTL basically stands for Register Transfer Level, and it's a critical abbreviation used in the digital circuit design, specifically in the VLSI field. So this RTL design serves as a bridge between the high-level system specification and the actual hardware implementation for digital circuit. As I've already discussed in my previous videos, that before coding the design using SDL, we do top-level specification design and test it using the high-level language like C, C++, MATLAB. And once it is tested, we move to the SDL for SDL language like Verilog or VSDL for a design cycle for the digital design. So this RTL descriptions are used as an input to synthesis tool, which transform the high-level RTL descriptions into a gate-level representation. These gate-level representation comprises of actual logic gates that are coming from the library files like AND gate, OR gate, which are suitable for the manufacturing or in the fabrication uh, companies. This synthesis process also optimizes the design for factors like area, power, consumption, and timing constraints. So, in short, if I say this netlist basically captures the logical and electrical connection between the components. So, once all those input files are given to the static timing analysis tool does the analysis and gives the output in the form of a timing report. So engineer basically go and check the timing report and decide based on the timing report that what has to be improved or optimized in the design. So now we will see the steps after which static time analysis is done in the design cycle. So this whole design flow is divided into two parts, front end and back end. So once the RTL is finalized and it's verified by the verification engineer, it goes to the next step of our design flow, which is called synthesis. So synthesis in VLSI is a process of converting your RTL code into a circuit or a gate level netlist. That synthesis, as you can see here, it's taking the SDZ file also. So this SDZ file, as I've already discussed, consists of lot of constraints that are required that the designer wants the design to meet. So synthesis take these input and optimize the design based on the predefined constraints that are defined in the SDZ file. Also, it allows the same SL description file or the RTL file to be mapped into different target technology without requiring any design change. So that technology information is described in the .lib file that I've already mentioned in the input to ST. Now, once these inputs are provided to the synthesis tool and it converts the RTL into a gate level netlist, it goes to the logic optimization tool. So whatever optimization that I was telling you that the tool basically do to meet the constraints is done in the logic optimization step. So as you can see here, after synthesis, it tool basically do static time analysis, and that static time analysis based on the while load model. And also that gate level netlist that is created after the synthesis is unoptimized and there is no place and route done, and the analysis that you are doing is doing based on the wire load model, and the clock that is there in your that is defined in your netlist, or that is defined in your RTL itself, or the gate level netlist is idle clock. So basically what it means with the idle clock is that there is no clock distribution tree all over the design. Another way, you can say that the clock signal is assumed to be present on time at all the clock pins. So based on these things, it do synthesis tool do the logic optimization, and this process goes on several times. So before moving forward, I'd like to explain what this wire load model also. So wire load model basically estimates the electrical delay and the capacitance associated with the on-chip interconnects. So as you can see that there's no place and route information, or I can say that there is no physical layout data present to the tool after the synthesis. So it will adopt wire load model to do the timing analysis. So in wire load model, basically estimates the wire characteristic in the absence of physical layout data. So while estimating, it estimates the electrical delay and capacitance associated with the on-chip interconnects, such as metal wires connecting to different components of the standard cells within the integrated circuits. It's an essential component in the analysis of signal propagation, delay and timing analysis of the digital circuit. So what, if in a layman language, I'll try to explain this. So wire load model helps engineer or tool to estimate how long will it take for a signal to travel through a wire in a digital circuit. It does this by looking at the number of pins that are connected to a wire and the length of the wire. So when I'm saying number of pin, you can say it basically checks the fan out of fan out of the wire that is connecting. This wire load model then uses this information to calculate how much time will it take for a signal to travel from one end of a wire to another. It's really important, because if the signal takes too long to travel through a chip from one end to another, it may cause errors or slow down the chip performance, and even in some case it can cause functional issues also, or functional issue, and then even the design may not work also. So as you can see here, this logic optimization is done based on the static timing analysis that is done using wire load model. So once this logic optimization is done, this netlist, which is optimized netlist, where no place and route is done, and the clock that we are using is the idle clock that I've already explained, goes to the backend of our design cycle. So in the backend, we'll use the spec file, which consists the parasitic information of our design. So that input I have already defined in the input to STA. So we'll move to the next step of a design cycle, which is called the floor planning and placement. So this floor planning basically involves planning the placement of various fundamental or functional blocks, such as logic gates, memory cells, and other components like macros, OTP. A lot of things are there in the design that you are designing. So that all those things, all those macros are properly placed there. So note that here you are not placing the standard cells. You're just placing the macros, hard macros, and doing the power planning of your design. Once that is done, the then it goes to the placement step. In the placement step, you place all the standard cells that are there defined in the gate level netlist after the logic optimization stage. So the So I can say the goal of the floor plan is to create a efficient, well-organized layout that meet the design rule and design goal and constraint. So as you can see here, that after floor planning, the gate level netlist that is created is placed, floor planning and placement. The gate level netlist that is created is placed, and the clock that we are using is idle clock only. After this step also, we do static timing analysis. But here, as we have some information about the standard cells that are there in our design, we do, instead of doing static timing analysis using while loop model, we do estimated parasitics. So we'll estimate the parasitic based on the standard cells that are placed in our design. And based on that, we'll do the timing analysis. And again, it goes to clock set again, and that information is given to the clock synthesis, which is the next step of our design cycle. One more thing that you had to appreciate here is that the gate level netlist that is created after the placement has idle clock, and the reason for this is that the clock is not stitched after the placement. So the actual switching of the clock happen in the clock tree synthesis. So clock tree synthesis basically is a process of generating a well-balanced and optimized clock distribution network within the IC. It does it by inserting buffers, inverters along the clock path of our circuit to balance the clock delay and reduce the clock skew of all the sequential circuit, or I can say it do it to balance the clock delay and reduce skew or clock skew of all the sequential elements that are present in your design. The aim of clock tree synthesis step is to minimize the routing resources, area, power consumed by the clock signals. So after clock tree synthesis, the gate level netlist that is present, that is an output for a clock tree synthesis. After the clock tree synthesis output is placed, and actual clock is present after the clock tree synthesis. So now, after this step of the design cycle, the design goes to the routing step. And in the routing step of the VLSI, or I can say routing in the VLSI is a process of making physical connection between the signal pins using metal layers. So it has several goals, such as minimizing the wire length, delay, area, vias connection, proper via connection between one metal layer to other metal layer should be there. Also, it checks timing, it checks design rule, and it checks that all those design rules that are specified by the tech left is properly meet or not. These metal layers that are used for the routing carries the signal information from one part of a circuit to another part. So after successfully routing, it goes to a RC parasitic extraction, and here after RC parasitic extraction, it goes to the static timing analysis, and here as you'll see, you are doing the static timing analysis using the extracted model that is done after the routing. So now at this step, you have all the information about the physical layout data, physical layout design, like routing information, clock information, standard cell information that is coming from the .lib file. All those information is used by the this RC parasitic extraction tool to extract the parasitics of a design. So in other way, I can say that this parasitic, if I just want to define this parasitic extraction in the VLSI for STA, it's basically it's a method to estimate the capacitance and resistance of the interconnects between the cell of the circuits, between different cells of the circuits. It uses it to perform the accurate timing analysis and optimize the design. So once this is done, you do PNR optimization or place and route optimization based on the STA reports that are coming after this. So once the design is optimized, it goes to the fabrication, and the design or the netlist that is created after PNR optimization is completely placed and routed. All the parasitics are defined, and actual clock is defined in the clock tree synthesis. So now, as you can see, that static timing analysis is implemented after every stage in the complete backend or even in the front end of our design also. So the reason why it is done after every stage of backend design flow and after synthesis also is that so that design can be checked for any violation that is coming after the states. So once the aim for doing the static timing analysis after every stage is so that whatever issues related to the timing that you are getting, you'll optimize or you'll resolve those issues at that step also or that step only. Because if you are not optimizing those timing issues after that step, it will accumulate and at the end of the routing when you are having exact parasitic after that if you are doing that timing extraction timing analysis, then it will be really hard to resolve those issues and it will be really time consuming and area consuming also. So in order to resolve those issues, we do static timing analysis throughout our design flow. So this is all. I hope you now understood that why static timing analysis is so important and why it is done throughout the cycle and what is the importance of static timing analysis. With that, I'll take your leave. Thank you very much. Please like, share, and subscribe.